So, we covered complex numbers, imaginary numbers on Monday with 4-1, and we're kind of continuing on with that, solving and trying to find solutions. And that's mainly what this chapter is. And really what we're leading to is something that we haven't done before, or y'all haven't worked with before, is some equations like this here, x to the 6 minus 1 equals 0, and trying to find the solutions for it, because that's going to be for 5, our last section that we cover in this here, because we could solve this by adding 1, then taking the 6th root of both sides, telling us x is equal to plus or minus the 6th root of 1 is 1, but that gives us 1 and negative 1, which is true. Because negative 1 to the 6th power is indeed 1. 1 to the 6th power is also 1. So we do have two of the solutions. But what we're starting with is here, the fundamental theorem of algebra implies that a polynomial equation of n degree has precisely n solutions in the complex number system. So it means it should have 6 solutions for this here. Well, with the methods we have so far to solve it, we only found 2, which means there's 4 others. And there are ways to find these. Specifically, it's going to involve using sine and cosine to find those other solutions, which we haven't had. You haven't had to do in Algebra 2. We haven't come across those yet. So that's what we're leading up to. Fundamental theorem of algebra, polynomial degree n, where n is greater than 0. F has at least one 0 in the complex number system. And that could mean that one of our solutions is, as we saw earlier, negative 1 plus 0i. It's now a complex number. So it could be that we have solutions and all we have to do is plus 0i and they are in a complex number system. Linear factorization theorem. If f of x is a polynomial of degree n where n is greater than 0, then f of x has precisely n linear factors, where c1, c2 to cn are complex numbers. We can write it in factored form. Now that could be that we have x plus 1, x minus 1, x plus 2i, x minus 2i. We have complex numbers or irrational. We have square roots, but we can write it out in this factored form. Now, if we do have these especially complex, or x minus the square root of 3, x plus the square root of 3, most of the imaginary complex and irrational solutions, we almost have to find them, then get them back into factored form. You almost have to know them to be able to find the factors. Deal. Now the next part, a first degree equation x minus 2 equals 0 has exactly one solution, x is 2. The second degree equation, x squared minus 6x plus 9 equals 0, if we factored it, we get x minus 3 and x minus 3, which means the solution, this equation has exactly 2 solutions, x is equal to 3 and x is equal to 3. Even though they are the exact same number, we count them as 2 solutions. They are just not unique. They're called repeated solutions. They show up twice. The fourth degree equation, x to the 4th minus 1 equals 0, has 4 solutions. 2 of them are 1 and negative 1, and the other 2 are I and negative I. We end up having 4 solutions for this here. So we still have 4 solutions. 2 of them are real, 2 of them are complex. And it always works at the degree. Whatever the degree is the number of solutions that we have. And that's kind of helpful because if I graph this here, x to the 4th minus 1, y equals x to the 4th minus 1 graph. I see it crosses the x-axis in 2 places, telling me 2 of the solutions are negative 1 and 1. I know I need 2 more. I found 2. Has to equal 4, so there should be 2 more left. So it is kind of helpful in determining the number of solutions for how many should show up. We also have the quadratic equation. If b squared minus 4ac is less than 0, we have 2 complex solutions. If b squared minus 4ac equals 0, then the equation has one repeated real solution. If b squared minus 4ac is greater than 0, the equation has two distinct solutions. We either have one repeated or two complex, two real, or one repeated solution. And this is kind of helpful because I know most textbooks don't really point this out too often, but I do find it handy is the square root of b squared minus 4ac. Because given any equation, especially if I'm trying to solve a quadratic, plus 6, here, and I want to see if it's factorable. If I don't want to go through the full process of finding the quadratic equation, I can plug the square root of b squared minus 4ac into the 30xs. Well, a in our case is 1, b is -5, and c is +6. So I can grab this, a second square root, -5 squared minus 4 times 1 times 6. Enter. And it is 1. And it works out that if I take the square root of b squared minus 4ac for any quadratic, and I get a whole number, well, we can say, yeah, whole number, because if it's 0 or any of our counting numbers greater than 0, we don't get a decimal, we don't get an error, because 30xs can't take the square root of a negative number. It means it's factorable. In that, whatever this comes out to be would be 1. I can add those two and divide. I can subtract those two and divide, which means this polynomial, this quadratic, is factorable. Actually works out to be x minus 3 and x minus 2, but there are ways to factor it. Does that kind of make sense? If it comes out to a decimal, a non-repeating, non-terminating decimal, it means radicals are involved, and we can't take this factor or factor it easily. If it gives an error, invalid domain, it means the solutions for this are complex. It has I, which means really we can still factor in both cases, but we almost have to know the solutions to be able to factor it. Ends up being, okay, we find out that it's 2 minus I and x equals 2 plus I. I have to solve it and work backwards, getting these back equal to 0. Same thing here. And then we just say that it is this here. Essentially, we found the solutions, got them equal to 0, multiplied those two back together, and those are our factors. And the same thing is true with radicals. We almost need to know the solution, get it back equal to 0, multiply them together to get our factors. All right. Well, that leads us to this part here. Use the discriminant to determine the number of real and imaginary solutions. Well, all we need to do is find the discriminant, our b squared minus 4ac. So here, the value of b is -20. Value of a is 4. Value of c is 25. Squared minus 4 times 4 times 25 is 0. Which means there is 2 repeated real solutions. Really, there's one unique solution, but they're both real. The equation has one repeated real solution, so technically they would probably want 1. Yeah, because the way I've written it, it's 1. We have 2 real solutions, but they're repeated, so it's 1. But that's it. Questions on this here? Now, one thing we could have done with this problem that we didn't especially, this is semantics. At this point, when typing it into the calculator, I could have dropped the parentheses and the negative and got the same answer. And the reason we can do this is negative 20 squared. Well, we know the negative is going to become positive. And since I know squaring that number will make it positive, I don't have to put parentheses in the negative because I know it will be positive. But if you're not sure if you need them or not, it's better to go and put the parentheses in the negative and then square it than it is to not. Because sometimes it's better to need it or have it and not need it than need it and not have it. Does that make sense? We can look at the next one. B squared minus 4AC. B in our case is 7. A is 13. C is 2. And again, we can type it in. 7 squared minus 4 times 13 times 2 is I still have a tendency to call them complex solutions. They are two imaginary solutions. The reason that there would be any distinction between the two is that the solutions when you get back, pull the door. Is that the solutions could be just I terms, like 2i, 3i kind of deal, where a complex number is technically a real number plus or minus an imaginary number. But I end up deferring back to complex. The last one, 5x squared minus 8x. B squared minus 4AC. Our B would be negative 8. Our A would be 5. And what would C be? Since there is not a constant term, a number without x being added or subtracted from our 5x squared and negative 8x, it is 0. Well, we can actually do this one by hand pretty easily, because our 4 times 5 times 0 is just negative 8 squared. 8 squared is 64. And since it is positive 64, it's greater than 0, we have two real solutions. And that's it with those there. Solve x squared plus 2x plus 2 equals 0, write complex solutions in standard form. What they mean by that is that x is equal to a plus bi, or x is equal to a minus bi. We need them in this form. Or if we wanted to, we can write them as a single term as a plus or minus bi. And according to the complex conjugate theorem, if a plus bi is a solution, a minus bi is a solution. If we have one, we have to have the other. We have to have its complex conjugate. Now, x squared plus 2x plus 2, one place I always default to is graphing. X squared plus x plus 2, I believe, is our equation. Does not cross the x-axis. So what that's telling us is that this here has complex solutions. And there's going to be, well, x squared tells me the degree is 2, so there should be 2. And since it doesn't cross the x-axis, it means both of them are complex numbers. So what we can do is use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Negative b would be negative 2. We can put the parentheses around it, but I feel like at this point, we feel pretty comfortable switching the sign with b. Since b was positive, it's now negative. If b had been negative, it would now be positive. The other one I feel we can do is the denominator, 2 times a. Well, the a value in our case is 1, and 2 times 1 is 2. Out of the quadratic formula, the only two things I do at the same time as plugging the numbers in is negative b in front and 2a. Because switching the sign and multiplying something by 2, I think at this point we can handle pretty well. What's inside the radical, I go on and write it out every single time. B squared, so we'd have 2 squared minus 4 times a times c. Next thing I would do is find out what inside the radical is going to be. So our 2 squared minus 4 times 1 times 2 is negative 4. Now I don't type the square root of our 2 squared minus 4 times 1 times 2 into the 30xs because, as we just saw, what's inside the radical is negative. The 30xs will not simplify that. It can't do negatives inside of an even root. The graphing calculator can take the square root of negative 4, and here we're in a good position because 4 is a perfect square. It'll take it simply. But if it had been something other than negative 4, let's say negative 5, it would turn it into a decimal. Then we've kind of got to work backwards to figure out what it is. So I always take it in these parts. Now the negative inside the radical, I know is going to come out as I, and the square root of 4 is 2. Now at this point here, we do need to do some simplifying. Part of standard form is that we split this apart, and that we say that we have negative 2 over 2 plus or minus 2 over 2 I, because this is considered standard form, a plus or minus b I. Well, our negative 2 over 2 is negative 1. 2 over 2 is 1 I. Or we just say that the solution is x is equal to negative 1 plus or minus I is our solution. And that's it there. Questions on this here? But really, we could have gone from here to here because we can see that all 3 are divisible by 2. So I just divide 2 out of all 3, getting us to there. Some of the reasons that we would need to do this middle step is if both terms are not divisible by the same amount or we have differing values. The only way that we will have a number that is reducible by all 3 spots and still have fractions is if the value of a is something other than 1. That's the only way the denominator can be greater than 2 for that. Or the 2 numerators, one of them is an even number and the other is odd. Then we can have a fraction and a whole number. But questions on this here? X squared minus 4x plus 5. X squared minus 4x plus 5. Graph. Again, complex numbers, because it doesn't cross the x-axis. So again, going back to the quadratic formula. So the first part, negative b, well in this case our value b is negative 4. So negative 4 is 4. 2 times a, well a is still 1, just like the last one, and 2 times 1 is 2. B squared minus 4a c goes inside this here. Now looking at this here, we already know we're going to have complex solutions, yes? What's going to give us a bigger product if we just were looking at it and hadn't seen the graph? Negative 4 squared or 4 times 1 times 5? Because 4 squared is what? 4 times 4. 4 times 1 is 4 times 5 is 4 times 5. Well, 20. Because 20 times 1 is still 20. Well, Our 4 times 1 times 5 is the bigger number, yes? And because 1 and 5 are either one of them are negative, it means we're subtracting 16 from 20. Incidentally enough, even though we're given different values, we end up with -4. So now being able to see that is not crucial. Being able to see which one's bigger is not a thing that is something that you have to know, but it's sometimes helpful. It's one of those things that helps you get an expected outcome. You know what's probably going to happen, so you can know which path you're probably going to take. Now at this point here, we need to simplify the radical. And again, just like the last one, the negative will come out as I, and the square root of 4 is 2. And well, we can split it up, but we do know that the two terms are divisible by 2. 4 divided by 2 is 2. 2i divided by 2 is I. So it's just saying that this here is equal to, for this one here, x is equal to 2 plus or minus I. Questions on this here? Yes? No? Complex solutions occur in complex pairs. We already said this. I got ahead of myself on this here. If a plus bi is a solution where b is different from 0, we actually have an imaginary part, is a solution of a polynomial equation with real coefficients, then the conjugate a minus bi is also a solution. If we have one, we have to have the other. They always come in pairs. So if we want to solve x to the 4th minus x squared minus 20 equals 0, well, y equals x to the 4th minus x squared, was it 20? And it was just, yep, graph. We do have two solutions, they just are not integers, but we do have two solutions, and most likely means the other two are complex, because we've had at least two complex in all of these here. Now this is something that we've covered before. We've talked about being able to factor these here. It is possible to factor it. I would stay away from using the quadratic formula on this here because we end up with radicals inside of radicals. But I'm going to use u substitution, and I'm going to set u equal to whatever the middle term is, middle variable. In this case, it is x squared. Because for this half of this equation, x squared will become negative u minus 20. Now x to the 4th would be u squared. Because powers of powers multiply, so if we square u, squaring, which would be x squared squared, giving us x to the 4th. But now that we have it rewritten as u squared minus u minus 20, we can see how it factors a little bit easier. Two sets of parentheses with three spaces. Since the third term is negative, our signs are opposite. Factors of u squared would be u and u. Factors of 20, we have 1 and 20, 2 and 10, 4 and 5. And the first ones we can try first are 4 and 5. I'll make 4 positive and 5 negative. And if we check this here, 4 times negative 5, or not 4 times negative 5, u times negative 5 would be negative 5u. 4 times u is going to be plus 4u, which gives us a negative u. Is that the middle term we wanted? Yeah. So it's telling us that u plus 4 and u minus 5 are the two factors. And whenever we have two or more things multiplied together to equal 0, one of them must be 0. We have u plus 4 equals 0, u minus 5 is 0. At this point, we can go on and solve for u and then plug it back in. We can minus 4, telling us u is equal to -4. Here, we can add 5 to both sides, telling us u is equal to 5. Now, the reason we can just straight solve for u is because we don't have a quote-unquote middle term. We don't have an u squared and u, it's just u, so we can get those by themselves. Now, we weren't solving for u originally, we were solving for x, which means at this point we do need to plug our x back in, because u is x squared. So one of the statements is saying that x squared is equal to -4. And the other is saying that x squared is equal to 5. Square root theorem. Because we had x squared by itself, we can just square root both sides. Since the square root of x squared is x, is equal to plus or minus. Square root of 4 is 2, and the negative would come out as 9. So there are two solutions, because we know x is positive 2i and negative 2. We still have 2 more, because over here we can take the square root of both sides. X is equal to plus or minus the square root of 5. Again, 2 more solutions, giving us a total of 4. The degree was 4, so we have found all 4 solutions. Questions on this here? Any questions on anything we've covered so far? Now again, we can do the same thing here, because we can factor this, but I think it's going to be easier to just use substitution. And for most of these here, we'll set u equal to the middle term, something we can use to work or make these easier to work with. So setting u as x squared, it rewrites this to u squared plus 7u minus 18 is equal to 0. Since the third term is negative, our signs are opposite. The only factors for u squared are u and u. Factors for 18 are a few more than just u squared, because we have 1 and 18, 2 and 9, 3 and 6. Which ones do we want to try first? 2 and 9. Plug them in, and then we can check. U times -9 is -9u. 2 times u is plus 2u, giving us -7u. Well, that's almost what we want. It is the correct number, but wrong sign. In which case, all we need to do is flip the signs. Because if we flip the signs, u times 9 is now 9u. -2 times u is -2u, giving us a positive 7u. And again, just like before, we can keep solving from here, telling us that u minus 2 is equal to 0, and u plus 9 is 0. Well, if we solve each one of these here, we add 2 to both sides for this one here. It tells us that u is equal to positive 2. The other one, we can subtract 9 from both sides, telling us u is -9. Well, just like the previous one, we're not solving for u. We need to solve for the value of x. And when we plug it back in, we're told that x squared is 2, and x squared is -9. And just like the previous one, we can take the square root of both sides, telling us x is equal to plus or minus the square root of 2. And here we can take the square root of both sides, telling us x is equal to plus or minus 3i. Questions on any of this here? Now, if we wanted to check these, we could. Because what we can do is second square root 2 store x. Because what this does, square root of 2, we plug the number in that we want, store, and the variable. And for us in this mode of just doing normal calculations, it is now set the variable x as square root of 2. And our equation was x to the 4th plus 7x squared minus 18. And we wanted to see what values of x made it 0, and it is 0. Now the nice thing with using this store function is I can change it from positive square root of 2 to negative square root of 2. Negative square root of 2 store x. Come back up here, reselect it, and it will now plug in negative 2, negative square root of 2 for each x, and it shows that it is 0. We also had 3i as a solution. So I can store it as x is value, have it plug it in, and it shows us that it is indeed 0. And then we can do negative 3i, store x, enter. And it shows us it is also true. So this is just a way to be able to check it. If we don't remember the order to do that, I can do parentheses negative 3i to the 4th plus 7 parentheses negative 3i squared minus 18. I can also plug it in for x. Either way, it'll show us that these are indeed the solutions. All right. One other thing they'll do for us is this here. Now, the reason they're doing this, or this setup, is because it's going to be difficult to find all the solutions, but we can. Because it wants us to find all the zeros. So real, complex, rational, irrational, it wants us to find them all. For f of x equals x to the 4th minus 3x cubed plus 6x squared plus 2x minus 16. Given that is 1 plus 3i is a 0 of f. That is an odd way to say that, but there you have it. Because complex zeros occur in conjugate pairs, we know that 1 minus 3i is a solution also. This means both x minus 1 plus 3i and x minus 1 minus 3i are factors. Okay, so this is the one they gave us. Since they told us one of the solutions is equal to 1 plus 3i. It also means x is equal to 1 minus 3i. If we have one, we have to have the other. Now the total number of solutions that we should have is 4, the same as the degree. And the nice thing is, given these two, we're halfway there. We have 2 of the solutions. Again, x to the 4th minus 3 x squared plus 6 or 3x cubed 3x cubed plus 6x squared. Is it 20x? 2x minus 60 plus 2x minus 60. I believe this is the correct equation, yes? Graph. We see it does cross the x-axis in 2 places. Well, we have negative 2 and 0. We're looking for when y is 0, so negative 2 is 1 and 3. would be the other 2. And we have a total of, so we are done. Now, the other way to have done this, and I think the way that they would want us to do this, is not to graph it. What they're wanting us to do, and we'll do it this way so that we see both, is this only works if if the other 2 solutions are integers, positive, negative, numbers without a decimal. So what they actually want us to do is division. They want us to do long division with this here. Now to do it is taking both of these here. Okay. Take 3. Getting them equal to 0 and multiplying them together, and then doing long division with the result. So to do that, first thing we would do is subtract 1. Then we would subtract 3i, telling us x minus 1 minus 3i is 0. For the other case, again, we would minus 1, telling us x minus 1 is equal to negative 3i. Add 3i to both sides, telling us x minus 1 plus 3i is equal to 0. At this point here, we would multiply them back together. And it kind of dawns on me, the reason this seems odd why we're doing this. Well, the reason we're doing all this is to find the number or the expression that we can divide x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60 by to reduce it. And anytime we do long division, synthetic division, we reduce the degree of the polynomial by whatever the degree of what we're dividing by it is. And here, when we multiply these 2 back together, we would have a degree 2, which would reduce our quartic equation down to a quadratic, and we can either factor it or use the quadratic formula to solve from there. And that is big with higher degree polynomial functions, is finding enough solutions to either get all of them or at least get it down to a quadratic. Because if we can do that, we can use the quadratic formula to solve from there. Now here, we're going to distribute out. X times x is x squared. X times negative 1 is negative x. X times positive 3i is 3xi. We can do the same thing with negative 1. Negative 1 times x is negative x. Negative 1 times negative 1 is plus 1. And negative 1 times positive 3i is negative 3i. And lastly, we'll do the same thing with negative 3i. Negative 3i times x is negative 3xi. Negative 3i times negative 1 is positive 3i. And negative 3i times positive 3i would be negative I squared, not I squared. If you'll hold, the rest of y'all can go. If you'll hold with me so I can finish this here, we'll be done for the day. We need to combine like terms. Negative x minus x is negative 2x. Our 3xi and negative 3xi will cancel. Negative 3i, positive 3i will cancel. Negative 9i squared. The I squared is negative 1. So negative 1 times negative 9 is positive 9. Giving us plus 10 is equal to 0. Now at this point here, we would place this up here, x squared minus 2x plus 10, and we would do our division. Okay. As much as I hate to stop here, well, we're going to stop here and we'll pick this up tomorrow because it's going to take still a few more minutes to do long division. If y'all remember doing long division with polynomial functions, I would rather stop at this point and pick up at this spot tomorrow than to try to rush through this at this point.